Hey everybody, this is a little video on how to, approach solving these horizontal projectile problems that are in your next assignment. And your next assignment is going to be this Unit 6 Concept Practice 3. So just a quick review about horizontal projectiles in general. Remember, as projectiles move through the air, the only force acting on them is the Earth pulling them down. So you can see I drew all of these little downward acceleration vectors here. That's the way the thing is accelerating. These are the horizontal velocity vectors. The horizontal velocity never changes. The thing moves steadily to the side no matter what. But the vertical part of the velocity keeps increasing, increasing, increasing. That's why it moves through a parabola. It's kind of useful if you can see that these two motions happen, apart from one another. It just keeps moving sideways steadily as it falls increasingly faster. The horizontal part of the motion, which I put in this circle right here, some details about it, it's constant velocity. It keeps moving sideways steadily. The vertical motion, which happens at the same time, is constant acceleration. It's always speeding up as it moves towards the ground. The only common thing between the horizontal motion and the vertical motion is the time that it takes. That's the only common thing that the horizontal motion has with the vertical motion. Now, generically, it's always easiest to say that the thing begins with an initial horizontal and vertical position of 0. So put the origin here. So we're working in this quadrant down here, that's the fourth quadrant, right? Don't they go counterclockwise? I'm pretty sure they do. Anyways, regardless of what quadrant you want to call it, you can always fill in a data table like this for one of these projectile problems. Now, make sure you start it at the origin, so initial x and y position is 0. You'll usually be told something like, how long it took. Maybe you'll be given that piece of info. Maybe you'll be given, where it landed sideways, how far it landed downwards. This is very generic. You could use this to solve pretty much any horizontal projectile problem. We'll get into a more specific one in just a moment here. Another thing, the horizontal acceleration is 0. There are no horizontal forces acting on the thing as it moves. But the vertical acceleration is negative 10 meters per second squared, always. That's the free fall acceleration. Now, a more specific example I can give you would be the first question from your new assignment. The question says, the movie The Gods Must Be Crazy begins with a pilot dropping a bottle out of an airplane. It is recovered by a surprised native below who thinks it is a message from the gods. If the plane from which the bottle was dropped was flying at a height of 500 meters, and the bottle lands 400 meters horizontally from the initial dropping point, how fast was the plane flying when the bottle was released? So just some information that I could glean from this from reading it. We need to find how fast the plane was flying when the bottle was released. So our unknown is going to be this horizontal velocity. We want to find that. You were told that the bottle was dropped while the plane was flying at a height of 500 meters. Well, why don't we go ahead and say that the initial horizontal and vertical position is both 0. I'd fill that in my table. So it started at 0 meters horizontally. It started at 0 meters vertically. Make two separate data tables, one for each the vertical and horizontal. How far does the thing go horizontally as it moves? Well, that was given to us. It says the bottle lands 400 meters horizontally, so it goes 400 meters over while it falls. And it falls a height of 500 meters, so it ends up at that point. Notice 400 meters sideways, 500 meters down. That's this point right here. Now, since it was a projectile that was going horizontal at first, it was a plane flying horizontally when it was released, we know the initial vertical velocity is going to be 0 meters per second. We don't know how fast it was going vertically when it hit the ground. That wasn't given to us. We do know that while it's in the air, its vertical acceleration is going to be negative 10 meters per second squared. Since it's a projectile, it's in free fall. We also know that it won't have any acceleration horizontally while it flies. It's steady as she goes sideways. Let's see how we can approach this. We don't know how long it took to fall. That wasn't given to us. If we want to get how fast it's going sideways when it was released, we would need to know how far it went sideways. We have that, and we would need to know how long it took to hit the ground. So how long it went sideways for. That means we're going to have to get the time. Now, the time is the common thing between the horizontal motion and the vertical motion. So maybe we could use this vertical information to figure out how long it would take to fall, a height of 500 meters. So with this data table, I can use any of my kinematics equations that I want. Here's a useful one that we've used a whole bunch of times in the past. Y equals y naught plus vy naught t plus 1/2 a t squared. That should be a familiar one to you. We usually use it with x's in it, but it works for vertical as well. If we say it started at the origin, that cancels. It was not moving up or down to begin with. That term cancels. We know what the acceleration is. It's negative 10. We know how far it moved downwards. So the only thing that's really left here is t. So let me rewrite this with the other things canceled. 1/2 a t squared. Now if I want to solve this and find t, I would take my half, multiply each side by 2. 2y over a equals t squared. So t itself must be the square root of 2y over a. So if I plug my values in here, t equals the square root of 2 times y. Now this thing went 500 meters down. That's its final y position. So that would be negative 1,000 meters, since it's 2y, over a, which is negative 10 meters per second squared. So negative 1,000 divided by negative 10 is 100, the square root of which is 10. And the units even pan out, the meters cancels, square root of seconds squared. So 10 seconds is how long it takes the bottle to fall. Well, not only did the bottle fall for 10 seconds after it was released, additionally, the bottle moved sideways during that 10 seconds. So now that I know my time is 10 seconds, I can go back over here. I know it moved 400 meters sideways in 10 seconds. So I could take this same equation, apply it to the x direction. We say it started at the origin. This is what I want. I want to know how fast it was moving at the beginning, because it stays moving that speed. And I know horizontally there's no acceleration. So this is what my equation turns into. I want velocity, so I'm just simply going to take x and divide it by t. X is how far it went to the side. That's the final x position. It went 400 meters. And we know that it took 10 seconds to do so. So 40 meters per second must have been the velocity sideways of the bottle. That's how fast the airplane was moving when they released the bottle. You guys will find as you go through this assignment, all of these problems involve a horizontally launched projectile. Sometimes you're given different tidbits of information. You've got to make 2 nice data tables here, one for the horizontal and one for the vertical quantities. Make a little sketch if necessary, and understand that the time that the thing moves horizontally is the same as the time that the thing moves, vertically is the same that the time it moves horizontally. You should be able to use these familiar equations and data tables like this to answer all of these. I'm going to go ahead and put the answers to each question in in the document so that you can look and see. And I'll also put that on Google Classroom for you to see. It's not on your paper copy that you have if you're working off of your packet for the unit, but go ahead and click on the link that's in the agenda and you'll be able to see the answers to these to see if you did them right. Hope you're having a good day, folks.